Yes, we're down here at Module 11 talking about application logic. Then there's just 2 more classes and a final exam. This class is nearly over. A lot of students probably already have enough points to have an A, and if that's true, you don't need to do more projects or take the final exam if you don't want to. That's normal in my classes. If you do extra hands-on projects, it can make up for everything else, and a lot of people just do a few extra projects, and that's enough to make up for what they would have made on the final. I think the hands-on is the most important thing, so that's fine. Anyway, so let's take a look at this logic stuff. I don't have any Kahoots because there are actually no general principles here you can put in a Kahoot, but it is just a tale of stories of real pen tests that the authors did. And for this, you learn valuable lessons, and I must say they've been valuable to me in my corporate training. I influenced the training a lot. I said you can have scanners. There's 3 ways to test your website for vulnerabilities. There's static analysis, where you run the code through a code scanner that just looks for patterns of source code that are bad. Then there's dynamic analysis, where you send requests to it from a scanner, like Invicti is one of them, that will just send a bunch of requests and try to see if it finds cross-site scripting and SQL injection and all that. And that's fine, but you also have to have human testing, manual testing, to look for logic flaws, because the scanners do not understand your application. They do not understand what it's trying to accomplish and what its importance to the business is and how the steps are supposed to fit together. So automated tests can never test for these logic flaws. And you need a human intelligence here, at least at the moment. So that's the point. There's no common signature, and it comes from an assumptions that developers have made, and it's often an assumption developers didn't realize they were making. They wrote code just assuming that the input would be like they expected, and there was some possibility of some unexpected input they didn't think of, and that led to a hole. So here's some real-world logic flaws. So here you have a remember me function. When you log in, you can check a box, remember me, so that puts a cookie on your machine, which is normal. But instead of the cookie just being a random number, which is the best practice, they put an encrypted string that contains your name, user ID, and volatile data, including your machine IP address. Okay, so this is pretty good. The fact that it includes your IP address is pretty good. That means somebody cannot copy your cookie and run it from a different machine. So this by itself is not that bad, but the other thing is they also saved your screen name in an encrypted form, and I guess in a cookie. And that's the problem, because they used the same encryption algorithm for both of these. And so they used the same encryption algorithm for a low priority activity to obfuscate a screen name, and for a high security activity to obfuscate the identity of a current session. And so the user can control the screen name, and the app decrypts that cookie, showing the results on the screen. So what you do is you copy the remember me cookie into the screen name cookie. The app decrypts it, and now you can see the decrypted result. So here's it has the name of the user, and then an IP address, and then some other numbers you don't know. So you change your screen name to the content you want, admin, and all the rest, and then it will encrypt it for you and give you the right cookie. So even though you do not know how to do the encryption, you don't have the key, and the encryption is triple dash, which is uncrackable, you can use the program to encrypt it and decrypt it. And this, by the way, is what I usually do when I'm doing malware analysis. I find their encryption and decryption routine and just use it. I don't even need to understand it. If I can find it, I can feed in data, and especially PHP malware, that works a lot. So this is a flaw. And you can see there was no SQL injection, no cross-site scripting, nothing for a scanner to find here. There was just a logic flaw, that an encryption routine was used forward in one place and backward in another place, and there was a way for a smart attacker to exploit that. It reminds me of a thing that got me $10,000 from Facebook. They found at Facebook that if you did a password reset, it would email you a link to click. Click on this link to reset your password, and it had this long random number. But that number was not generated uniquely there. It was used somewhere else on the Facebook page. You could go someplace like to images on the page, and there was something there that included that same number. So you could examine somebody's page and predict what the number would be when they did a reset, and you could forge the reset token and reset somebody else's password, because whatever process they used to create that was used again in another part of the page, which exposed it. A very similar problem. So here's the steps. You look for things that are encrypted, not hashed. Substitute other encrypted values and see if you can cause some kind of error that reveals the decrypted value. All right. So then there's a password change function. So when you're doing password change, it asks for username, existing password, new password, and a second copy of the new password. This is a typical password change form. But the administrators can change a password without putting in the old password. And the way it was implemented by Real Product, an AOL product, was the administrator's form doesn't ask for existing password. It asks only for username and the new password. So all you have to do when a request comes in, it looks to see if the old password is there. And if it's not there, it assumes you're the administrator, because the administrator's form is the one that didn't ask for it. This is the same mistake almost everybody makes. They put up a form, then they send a request to the server, and the developer assumed that the data sent to the server came from that form and was not modified by something like Burp. So they're trusting essentially client-side restrictions. So you submit a password change without an existing password. Now you're the administrator. You can reset anybody's password. And this happened in the AOL Enterprise Gateway application. A lot of these things happen in big, important applications. Like I probably mentioned before, about 12 years ago, Solaris had a version for 6 months where if you remotely logged in as root, it would not check the password at all. You would always get in with any password. And it was that way for 6 months before anybody noticed. A lot of incredible stuff will go by. So you can do this by just deleting parameters one by one to see what happens with requests without all the parameters filled in. And here's another one, just doing things in order. So you add items to your shopping basket, then you go to the shopping basket and finalize the order, then you enter payment information, then you enter delivery information. But the developer can assume these happen in order, but you might be able to just skip from 2 to 4. Not bother to enter payment information, skip to the 4th page, and now you can get the product without actually paying for it. And if we talked about this before, you can enforce this by having a hidden form field that's random on each page, so you'll only accept a request to step 2 that came from step 1. And a request to step 4 that did not come from step 3 would not be accepted, but you have to add that in to the form, and that wasn't here. So I call that forced browsing, where you jump to a page without going through the expected steps. So whenever there's a series of stages, try doing a single stage more than once, try doing them out of order, try skipping ones, and see what happens. Guess what assumptions the developer made and violate them. All right, and here's another one that's kind of complicated, but this is one where users could obtain quotes for insurance and submit an application for insurance. It had a lot of stages. So you fill out basic information, the app computes any values you didn't specify, then you give it your health, occupation, and other information, and then it sends it to an underwriter. Now the underwriter is someone using the same web app to record whether they approve your request or not. So they're going to make, they'll examine it and then tell you how much it's going to cost to get that much insurance or something. All right. So the assumption is each request will contain only the parameters requested in the current HTML form. They did not consider a user that submits extra parameters, which is the very common theme here. So what the attack is, you supply valid data in an earlier stage, but then later on you override it, resetting the same value that was set on a previous form. And the validation only happens on the first page. So some places ask for your address, you put in your address. It checks your address to make sure it doesn't contain cross-site scripting or something, but only at that page. If you then change the address on a later form that isn't asking for your address, it will take the data, but it no longer validates it. That's the flaw here. So now I could do a cross-site scripting injection and reveal personal information of applicants. I could also purchase insurance at an arbitrary price and change the monthly premium, because I could request unreasonable stuff and then the underwriter will disapprove it, but I can then go back to a later stage and feed in the parameters from the underwriter that says like reject and change it to approve. Because the underwriter and the customer were using the same form, the same app, different forms on the same app. So that's the game. So if you put in unexpected parameters on unexpected pages, you might get away with things. And here's another one. The app is letting existing customers register for online banking. So they had a highly secure system where they would mail you some paper containing instructions to log in and a one-time password to try to make sure that only the authorized user would get it. So they intended to be safe. It requires some personal data. It mailed you a one-time password. So that's basically two-factor authentication now. And the customer has to call in and authenticate something that they, from the mail packet. So the problem is the customer information is here, just a lot of customer information. And what you can do is you can make an account and then change. Once you've logged in with valid credentials, you can go and submit different customers' personal information. Change your name and address to somebody else's name and address. And that's got one object for every customer. So we'll overwrite this with a new object to the targeted customer, and now you have access to the other person's account. This is a sort of database flaw. There's a customer record, and when you change your customer record so it matches another customer record, it will now go to the other person. There's a related thing that came up in the textbook, which I tried at Phil's Coffee, where they said if you can make two accounts with the same name, they might go to the same place. And that was not true at Phil's Coffee. I was able to make an administrator account, but it didn't get administrator privileges. So there was a hidden unique identity number. And here apparently there was not a hidden identity number. It was actually identifying you just by this information. So if I put in information that matches an existing customer, it will let me in that existing customer's place. This is why everybody gives you a special number for every business. You have a Safeway number, you have a City College number. Everybody has to have a unique number identifying you to avoid this kind of thing. All right. Anyway, that's the fundamental flaw. All right, and then there's beating a business limit. There was a guy that, this happens a lot, where there's limitations and you get around them. So here you got you can transfer funds, but you can only, most users are blocked from performing transfers over $10,000. If you want more than $10,000, you have to get a manager to approve it. But here's the test. It checks to make sure that if your amount is below the threshold, then it doesn't require approval. So that's fine, but the problem is they didn't think about negative amounts. So you can send a huge negative amount, it will go in the other direction and it will not require approval because it passes. This is quite common. Negative amounts and really large amounts. Also, if it's stored in the wrong kind of data, a really large amount will roll over and become a small amount. So that's why any kind of numerical value, there's a variety of these mistakes, negative numbers and overflows to check for. All right, so here's another one. A lot of numeric limits. You might only be able to order a certain amount of products. You might only be able to you can't make a bill payment that exceeds your balance. You may adjust your quotes. There's a lot of things where you have dollar amounts and ages and stuff, and you should try entering negative values and see what happens. Yeah?
How does the math work on the negative amounts, like to where the accounting system doesn't freak out? Are they passing through like double negatives?
No. Well, usually, in fact, in an app I wrote for this purpose, if you transfer from 1 to 2, a negative amount, the money goes from 2 to 1. It subtracts here and adds there.
Okay.
So, I mean, if you just say, because what you do is you have the amount, and then you add the amount to the first account, or subtract the amount from the first account and add the amount to the second account. And if it's negative, that math goes through just the same. It just moves the money in the other direction. But your tests to make sure it was not spending more than you had will not work. And that's why it's tricky. I mean, I had an app like this in one of my classes, and a student ran his account up to like $100 million and said, boy, I wish my bank had this app. And he was like, all right. And then here's one where you cheat on discounts. You order products, and if you get a whole bunch of items all together, you get a discount by buying all these different products all together. But what they did was, when you added them to the shopping basket, it applied the discount, and they didn't consider that you can then remove it from the basket. So you add all the junk to the basket, you get the discount, then you remove most of it, but you still have the discount. This is really common. I remember another one that was really common is you could get like a free USB drive from Microsoft, and all you had to do was log in from another IP address, and you could get another one, so you could just write a bot and use something like Tor and get as many as you wanted. This kind of thing happens all the time.
I think that happened to Amazon.
Yeah, and it happens with all online voting and polls. Like any kind of poll and voting, somebody can just write a bot that comes in from like Tor and votes many times. That's a fundamental problem with any kind of online system like that. All right, and this one is pretty funny. So developer lets user-controlled input go into an operating system command, like the ping that I did before, directory, but they're trying to avoid the code injection, so they added a backslash to escape all the special characters. But they forgot to backslash the backslash. They didn't think that would do anything, but it did. So what you have to do, this is the injection, foo backslash semicolon ls. Now a backslash removes the special properties of a character. So a backslash semicolon will just be treated as a printable character semicolon like any other letter. It will not have the property of separating two commands. But the application backslashes the semicolon, but it doesn't backslash the backslash. So the application will turn it into this. And in this case, the backslash will remove the special property of the second backslash. So it'll just be a character, and then the semicolon takes effect. So that's the problem. By failing to backslash the backslash, I can inject a backslash and then get away with injecting a character. So this is why deny listing like this is really dangerous. It is very hard to write a good enough deny list that a smart attacker can't get around. Allow lists are much better, where you only allow things that you know are good and block everything else. All right, and so here's another one. So they have an input validation system, and they want to not let you input in quotes because they're worried about SQL injection. So if you change quotes to two quotes, then that's the SQL symbol for a quote, a literal quote, like a backslash. It treats it a literal quote, not a meta character that terminates the line. But then there's a length limit, truncating all characters, so the length limit can undo this. So what you do, this input, for example, if you try to inject that, which you've done before, it'll turn to this. It will change the apostrophe into a double apostrophe. And that will be interpreted as a literal apostrophe. Admin apostrophe dash dash. This will be interpreted as a real name it's going to look for, so it will not perform SQL injection. Instead of letting you in by having username equal admin and then commenting out the rest of the line, it will look for a name, admin apostrophe dash dash, and what that person's password. So it defeats SQL injection, so it does accomplish the goal of the developer. The problem is, if you put in 127 A's followed by a single quotation mark, then it adds another apostrophe, but the length limit removes it. So now you get a syntax error because you have the wrong number of apostrophes here. And now you can now submit the same username and a password like this, and now you'll get username equals this, and this will be interpreted as an apostrophe, and the end password will be interpreted as part of the username. This will all be interpreted as part of the username. And then the or 1 equals 1 that you fed in with the password will get in there, so now you'll get everything. You'll get all this is a condition that will always be true. So anyway, that's the point. A length limit could undo the other defense, which involved increasing length. Sort of thing happens a lot. So if you want to find this, submit strings like that and look for errors. All right, and here's another one where you had a search engine which had access to an archive. This is in the CISSP class 2. That's an inference attack against the database. So you can perform a query, but you must pay to read the found articles. So the question is, can I learn something about these articles without paying? And the answer is you can. The titles are cryptic things like this, but if you can guess things about the title, you can, like blind SQL injection, you can guess until you find information. So here he is, press release, 0 matches, press release, 0 matches, but here there's one match for press release with takeover. So there is a match, including those words. So now I can try adding more words here, Haxor's Inc. One match. Now I have takeover NGS, okay? So now I'm deducing information about the article just by guessing and seeing how many matches there are. Even though I'm not allowed to read the articles, just the fact that I can see how many hits there are means I can eventually brute force my way in. So that's an inference attack. In the CISSP land, they call this data aggregation, I think, where you have low privileges. You can only do this kind of query, but you can deduce a high privilege fact from many low privilege queries. For example, a simple case is where you have a Centrex phone number, where you only dial 4 digits, and some of those numbers are restricted, not in the general phone book. So you can just dial all the numbers in the phone book and figure out which ones are missing, and those must be the privileged ones, that sort of thing. That mattered more in the old days because it used to be that your routers had a special phone number to control the router, and that typically had no authentication at all. That was the second port on Cisco routers, called the aux port or something, and that you would just dial the special number to control the router, and they thought nobody would figure that out. All right. That, by the way, was true of BART. One of my visiting speakers was hired to do a pen test at BART, and so he was scanning the network, and he found this telnet port on one of the ports of the BART system, and so it just said a prompt. So he sent a 1, and it said 1. Then they put in 2, and it said 2. He said, okay, I don't know what that is. He went on, no password, no nothing. And then he went on with his pen test, and someone came knocking on the door. What are you doing in there? Well, I'm doing the pen test. Did you go to this port? I said, well, I did, but there was nothing there, so I went on. Okay, it must not be you. That was the master control switch for BART. 1 meant the trains run, 2 means the train shut down. He shut down the whole BART system for a whole day. It was on the front page of the Chronicle. BART went down for a whole day because of computer problems. That was the problem. And so this was a result of his pen test. You know, there should be a password on that. But this was the common practice at companies. You would just have a special port that you thought nobody would find, and you could just turn things on and off, control the router and things like that at that special port. Nobody put authentication on them until starting maybe 10 or 20 years ago. People started to wise up. That's why in 1980, when War Games came out, is when they had personal computers that could do war dialing. That was a big part of that movie. You could get like a Commodore 64 or something, or an Apple II, and you could dial all the phone numbers just automatically all night long, and it would record which ones had computers. People, until that time, people thought you couldn't find the computers because you don't put them in the phone book. How would anybody ever find that number? That was a big revelation at the time, that you could use a computer to dial like thousands of numbers until you found the interesting ones. And so a lot of people had a lot of security that just depended on nobody knowing the number. Anyway, so like I said, I used this before to brute force a password from a configurations file stored by just putting in stuff like this and seeing which ones are found. All right, and then you might have debug messages. If the app is new and it has detailed error messages giving you all the parameters that generated the error, they might think this is okay because you only see the errors that come from your session. And by the way, you might have noticed City College's Web 4 is like this. If I log into Web 4 to like enter grades or something, and then I come back an hour later, it's timed out, and it frequently gives me a whole page of like Oracle error messages and stuff. It often freaks out. But they usually don't care because those messages are about my session. So all I'm getting is my session details, which I could have got from Wireshark or looking in my browser or something. So that would be okay. But the problem is, it's my data. The problem is they didn't implement that properly on the server. What they did was they made a stored container for error messages in like the temp folder. So the error condition copies data to the container, and then it displays information from that container. So you have a race condition, a time of check to time of use. It copies data to the container, and then it reads the container to show it to me. There's a time gap between those two. Something might happen in that brief period of time. And so if two users have errors at the same time, it copies my data to the container, but then before it displays the data, another user's data goes in the container, so I might see somebody else's error message. And this kind of thing happens all the time. I remember years ago I saw somebody else's Yahoo Mail just once, and other people say they sometimes see somebody else's Gmail. You can see how it would happen with caches and stuff all over the place. Somehow you're fetching a page that is actually on another user loaded. So this was one flaw. There's a race condition, so sometimes users will see other users' data. But that actually is not a huge problem because it's only going to happen in periods of high traffic and only rarely. So that'll affect a few random users. But what's much worse is this. All you have to do is pull the error message over and over and over. And then you'll get everybody's requests. Log all the requests, and you'll get all the parameters people are sending up that result in errors. So you'll get usernames, session tokens, may have passwords and other things. By just pulling it, you'll just see a lot of error messages that should have been sent only to other people. All right. And here's one where you have a multi-stage login process where you have to supply several different credentials, and this was considered very secure. They had high confidence in it. So sometimes a user would log in and get a different user's account. They couldn't figure out what's going on. It seemed random. They eventually discovered it happens when two people come in at the same time, but not reliably. And so what happened is the application stored an identifier in a static non-session variable, like a temp variable. It should have been stored in a variable tied to their session. But instead, they stored it in some general container like the temp folder. And again, a race condition. They stored it and then read it back an instant later. But if another login wrote to it in between, you would get somebody else's account identifier. This is very common. You have to save something. I've done it all the time in my program. You save it in a temp folder, then you pull it back later. It's a bad practice for this reason. You should save it in some folder that's tied to that session if you have to do that. So that's a race condition, a brief moment of vulnerability. So you have to document your design and think about it. Consider your logic flaws. You have to have comments so you understand the purpose of the components and the assumptions made. And during a security review, consider the assumptions, imagine circumstances that violate these assumptions, and you have to think laterally about ways the app handles unexpected behavior and possible side effects. It takes practice. It's very hard to think out of the box. This is a cliche statement, but people start with assumptions. This happens to me all the time in capture the flag problems. I will read the problem, I will start solving it. It will get harder and harder until I'm working really hard because I'm on the wrong track. I'm digging a hole, I'm digging it deeper and deeper. I've made an assumption that was wrong, and you have to clear your head and try again. You have to reset, So it's hard to do. It's hard to get out of your assumptions. But with enough experience, you learn to recognize when you're banging your head on the wall, this is not working. It happened to me a lot when I'm developing projects. I'll start developing projects, it will get hard. I'm doing more stuff, and I finally say, well, I'm just going to go take a walk and try again. And say, I don't really have to do that project. Here's the goal. I'll find another way to do it that isn't so hard. Anyway, so that's the kind of thinking you have to do to overcome these logic flaws. And that's all the lecture I wanted to show you today. And I don't think I need to demonstrate more of these Web Security Academy ones. I think I'll just answer questions. So let me stop the recording and answer any questions that may come up.